This video is about the expectation of continuous random variables. Well, we know expected value of random variables assigned by the expectation if they exist, they are numbers. But the question is, how do we assign different numbers to different random variables to describe their average value? And here in this video particularly, we're going to discuss how do we link different numbers with continuous random variables to describe their average value. Right? What are the expectations of continuous random variables? Before we formally give the formal definition, let's take a look. How do we define the expectation of discrete random variables and see can we proceed from here to generalize the definition to continuous random variable? Okay, so this is the expectation of discrete random variables. For a discrete random variable x, the expectation of x essentially is a weighted sum of all possible values taken by this x. It's defined by the PMF function. Unfortunately, the PMF function is specifically defined for discrete random variable, and we don't have this for continuous random variable. However, there are two ways to specify the distributions of random variables. We can also rely on the CDF function, right? The cumulative distribution function, which is also well defined for the continuous random variables. So can we generalize this idea to calculate the expectation of continuous random variable, right? Making use of the CDF function there, okay? So for this specific case, for the discrete random variable case here, the delta fx, the difference in the value of the CDF function, here we can choose two different representations, right? One is fx minus the left limit of fy with y approaching to x from the left. In this scenario, in the discrete random variable scenario, that's equivalent to use this format, which is the difference of fx xi minus the fx xi minus 1, if we order all the outcomes in one increasing order. Then by the definition of PDF, we know the difference in the CDF function values is essentially the PMF function value. So how do we generalize the idea here, right? A weighted sum of possible values taken by x multiplied by the width equal to the difference in the CDF function to continuous random variable. Let's take a look at one example, right? To calculate the average waiting time. So how long do we need to wait until the first customer? Let's assume NT is the number of arrivals within time 0 to t, and NT follows Poisson distribution with arrival rate, Poisson distribution with arrival rate lambda t. Let T1 be the time until the first arrival. Then we know this event, T1 larger than T, is equal to NT equal to 0. If we have to wait more than over T for the first customer, that's basically say there's no one arrive, right? There's 0 arrivals within the time interval 0t, and we have to wait for more than t time. Thus, the probability of T1 strictly larger than T is essentially the probability P and T equal to 0 arrivals. And NT follows Poisson distribution here, making use the PMF function of Poisson. We know this gives this value, right? So the next question is, well, what is the CDF, of course, right? To specify the distribution, always look at the CDF. So here, the CDF of T1 is ft1t is essentially the probability value of T1 smaller or equal to T. We have already calculated the probability value of its complement event, which actually this one is a survival function, right? The CDF is equal to 1 minus the survival function, or we can say this probability value is simply 1 minus its the probability value of its complement event. Now we plug in. This gives the CDF function. Right now we have the distribution of this continuous random variable. Apparently T1 is a continuous random variable. It can take any values, any positive values in this case. Right? You could wait for 1 minute, 2 minutes, and keep going. So now the next question is, how do we generalize the idea of expectation of discrete random variables to calculate the average waiting time? Right? Do you have any ideas? You can pause the video at this moment and try to figure out some ideas yourself. Well, we can calculate the average waiting time by considering this approximation, by cutting time into pieces of unit length. T0 equals 0, T1 equal to 1. Well, it basically says, suppose this is the possible waiting time, right? It could be from 0 to 1, could be 2 and 3, and keep going. So the idea is, let's use the middle point to represent or to approximate the average value if the waiting time lies in this interval. So, for example, for the first interval, from 0 to 1, right? Well, the probability of waiting time lies in this interval is the probability value of T1 strictly larger than 0 and smaller or equal to 1, right? And we're gonna use the middle point in this interval to roughly approximate the average waiting time in this interval. It could also be possible from the second interval. It will be 3/2 times the probability that the waiting time lies in the second time interval of unit length, and we keep going. Right? We can use this as an approximation for the average waiting time. So in the end, we have a summation of infinite terms. This is infinite summation. So middle point of the interval times the probability that waiting time lies in that certain interval. And let's write it as a difference. Right? Now we link with the expectation of discrete random variables. Let's write this as a difference of the CDF function. So how do we proceed to the next step? Well, the question is, it's still very hard to calculate this summation, right? But if we look at this difference, this difference, let's draw a graph. For example, suppose this is the ft1 function, and this is ti, and this is ti plus 1. So somehow increase from here. So the difference between these two values, right, between the CDF function values, if we draw a tangent line here, right, if we so if we draw a derivative, right, the tangent line of this curve, note here the difference between these two function values is roughly, right, the tangent value of this angle times the length, the interval ti plus 1 minus ti, right? And we know the derivative of ft1 function evaluated at ti is equal to the tangent value of this angle, right? So the derivative times the difference roughly approximate times the length between ti and ti plus 1, right? The product of the derivative value at ti plus 1 minus ti is roughly equal to the difference. between the function values evaluated at ti plus 1 and ti, right? So let's consider another approximation, which is ti. Now we use this product to approximate the difference. And if we let this ti minus ti no longer equal to 1, but to be smaller and smaller, then we can use simply ti to approximate the middle value, right? Because now ti plus 1 is roughly close to ti. Okay, so we have an additional approximation for that. And this approximation actually is closer and closer to the average value of the waiting time, as long as we choose a smaller and smaller grace, right? If we choose a smaller and smaller length of the time interval. So previously, if we cut intervals of unit length, now we are cutting finer and finer grace and making the interval length to be smaller and smaller, right? Let's say this interval length to be decreasing to 0, shifting to 0. If we let ti plus 1 minus ti shifting to 0, if we look at this formula, that's exactly the definition of the Riemann integral of this function, t times the derivative of the CDF function. And this actually is the definition of expectation of a continuous random variable, okay? And given the connection between the CDF function and the density function, we know we can rewrite this integral, this Riemann integral in this format, right? The derivative, normally we choose the density function equal to the derivative of the CDF function, so it can be rewritten in this way. If I choose the derivative, if I choose this small function, density function equal to 0 for all negative value t's, then we can extend this definition, right? This integration to the whole real line. This way we actually define a general, this way we actually derive a general definition for the expectation of continuous real valued random variable. Let's take a look of the formal definition here. The expectation, expected value, first mode mean, average of continuous real valued random variable if exists with PDF f is defined by where this Riemann integral such that we're gonna integrate from negative infinity to positive infinity of this integrand, x multiplied by the density. Well, if we use a generalization of Riemann-Stieltjes integral, we can also rewrite this via the CDF function, right? It's requires some additional knowledge about integral theory. We are not discussing in this video, but I still leave it there because now we have two different ways of defining this expectation of continuous real valued random variable. And given we have two different ways describing the distributions, right? So I also leave the second way here. Not only we can define the expectation via the PDF function, which is specifically defined for continuous random variable, we can also define that with the CDF function. What are the nice properties of this one? Well, we still have the LOTUS, the law of the unconscious statistician. For random variable gx, we only need to know the distribution of x to calculate its average value. We don't have to derive the distributions, the CDFs or PDFs of this random variable gx. The expectation of gx is essentially, again, the integral, the Riemann integral that of this function. And we're gonna integrate this function from negative infinity to positive infinity, which delivers the expected value of gx. And we know for general expectation for general random variables, they have linearity, monotonicity. And indeed, here for this specific definition of expectation of continuous real-valued random variable, the Riemann integral, the properties of Riemann integral also imply the linearity and monotonicity. So they definitely also holds true for the expectation of continuous real-valued random variables. Okay, this is a short video discussing introducing the expectation of this continuous real-valued random variable. So in this video, we generalize the idea of expectation of discrete real-valued random variable to the expectation of continuous real-valued random variable. Hope you enjoy watching this video, and thank you for watching this video.